Today, we're going to build voice AI that's not just smart, but blazingly fast and, you won't believe it, actually affordable. We're going to break down a super powerful combo of 3 key technologies, and I'm going to show you the real-world performance and the actual price tags that make this possible, like right now.
Okay, so let's start with a problem we have all had. You call customer service, you get a voice bot, and you try to talk to it. But there's always that awkward pause, right? That clunky delay that just screams, "I'm a computer." It totally shatters the illusion. So what is actually going on there?
Well, it turns out there's a literal breaking point. Research shows that if the delays in a conversation stretches past 2 seconds, our trust in the interaction just plummets. It's the exact moment our brain flips a switch and we go from feeling like we're in a natural chat to feeling like we're just waiting for a slow machine to catch up. And that is the core problem we have to fix.
And that brings us perfectly to the first part of our solution, the latency breakthrough. Because before we can even talk about making AI cheap or efficient, we have got to make it fast. Fast enough to feel human.
You know, the reason older voice AI feels so sluggish is because it's usually monolithic. Think of it like a very inefficient assembly line. It has to wait to hear your entire sentence. Then it sends that whole chunk of audio away to be transcribed, waits for the full transcript to come back, sends that to the AI brain, gets the full text response back, and only then does it even start creating the audio for you to hear. Every single step has to finish before the next one can start, and all those little delays add up to one giant trust-destroying pause.
So, the metric that matters most here, the thing we absolutely have to optimize, is something called time to first audio, or TTFA. Now, this is not about how long it takes the AI to say its whole response. Nope. It's about how fast you hear the very first sound, the first syllable after you stop talking. That is what our brain registers as a quick, natural response.
And when you get this right, the difference is it's staggering. I mean, look at this chart. A traditional, monolithic system can take up to 27,000 milliseconds. That is a full 27 seconds, an eternity in conversation. But an asynchronous framework like LiveKit agents can get that time to first audio down to just 15 milliseconds. We are talking about an improvement of up to 1,800 times. That is the difference between an impossible conversation and one that feels totally natural.
So how in the world does it do that? Well, it uses a couple of really clever tricks. First is Instant Connect, which starts grabbing your audio the second you start talking, even while a connection is still being established behind the scenes. And second, and this is the real magic, is preemptive speech. The system doesn't wait for you to finish your sentence. It starts figuring out a response based on just the first few words you say. So by the time you're done talking, the AI is already a step ahead, ready to speak almost instantly.
Okay, so we've solved for speed. That's awesome. But how do we actually power these gigantic language models without needing a warehouse full of supercomputers? Well, that brings us to the next piece of our puzzle, the efficiency engine. So this right here reveals a massive kind of hidden problem inside most large language models. To remember the context of a conversation, they use this special memory called a KV cache. The issue is, traditional systems are just terrible at managing this memory. As you can see, a shocking 60 to 80% of the memory that's set aside for conversation is just wasted. It's allocated, but sitting there completely empty.
And this is where a brilliant system called vLLM comes in, with its key innovation, paged attention. The best way to think about it is like managing a hotel. A traditional system is like a really picky hotel manager. If a group of 10 people shows up, he insists they all get rooms in one single, long, connected row. If he only has 5 rooms here and 5 rooms there, he says, "Sorry, can't help you," even though the rooms are empty. Paged attention is the smart manager. It says, "No problem, I'll give you any 10 empty rooms, doesn't matter where they are." It fills every available space and eliminates all that waste.
And the result of being that smart and efficient, you can serve 2 to 4 times more requests on the exact same GPU. That is a gigantic boost in throughput. And more throughput means lower costs, because you're getting way more bang for your hardware buck.
But, and I cannot stress this enough, you have to set it up correctly. Just look at these numbers. One RTX 4090 GPU gets you almost 4,000 tokens per second. Not bad. But if you throw a second GPU in there and forget to set the tensor parallel size correctly, your performance gets cut in half. You're paying for 2 GPUs and getting less power than one. It's crazy. But with the right setting, boom, you jump up to almost 5,500. Configuration is absolutely critical.
All right, we have speed, we have efficiency.
But that brings us to the final, and maybe most important question for any real project. How do we actually pay for this? And this is where cost-effective scaling comes into play.
Platforms like RunPod are a total game changer here because they offer a serverless pay-per-use model for powerful GPUs. So instead of renting a GPU by the month 24/7, you only pay for the literal seconds that it's actually working. When nobody's using your service, it scales all the way down to zero and you pay nothing. For any app that has busy times and quiet times, this is so much cheaper than a fixed plan.
Let's make this real. Here's a heavy-duty example. Some researchers built a tool to automatically generate complex programming tests using a beast of a model, the 70 billion parameter Llama. You'd think that would be expensive, right? Well, a really demanding job that took about 20 minutes of GPU time cost them just €4. That's it. It proves that even incredibly intensive tasks can be surprisingly affordable.
And this isn't just a theory. This is happening in the real world. Here's the actual workflow diagram from that research paper. You can see the whole automated process. The code comes in from the left, it triggers a job where RunPod fires up the Llama model to do its thing, and then it pushes the new code right back. This stack is out there, in production, doing serious work as we speak.
So this leads to a really practical question. When does it make sense to build this yourself versus just using an API from a big company? Well, here's a great rule of thumb. When your monthly bill for one of those paper token APIs gets high enough that it could have paid for renting your own dedicated GPUs for 2 or 3 months, it's time to switch. That's the point where the math flips and self-hosting becomes way cheaper.
Okay, let's put it all together. We've looked at 3 different powerful pieces of technology. Now let's see how they assemble into one seamless, incredibly capable stack for next-generation voice AI.
So here it is, the whole picture. You've got LiveKit on top, solving the latency problem, giving you that instant human-like responsiveness. Then you have VLLM in the middle, solving the throughput problem by making your hardware insanely efficient with paged attention. And finally, you have RunPod as the foundation, solving the cost problem by letting you pay for only what you use. Each layer perfectly solves a critical piece of the puzzle.
And that brings us to today. For the very first time, building a truly conversational, human-like voice AI isn't just a technical fantasy, it's an economic reality. The biggest barriers, latency, throughput, and cost have been smashed. The question is no longer, can we do this? The question now is, what are we going to build with it?